Yeah. Hello, it's a great pleasure to invite Brian to give a mini course on Bruhat-Tits theory. Brian has been a collaborator and now he has become a family member. So, it's so nice to see him.
Okay, thanks very much for the invitation. So I just want to begin by saying that, I remember when I first arrived at the University of Michigan many years ago, and Gopal was teaching a course on the general structure theory of reductive groups, which I didn't know so well at that time. And I remember thinking to myself, oh, it'd be nice if, someday I could understand these things. And, I learned a tremendous amount from Gopal about many things related to algebraic groups. And so he and Tasha Clayton wrote this awesome book on Bruhat-Tits theory, which they give a new approach to developing the theory. Of course, the main results are the same as they were before, but much more understandable. So anyway, I encourage you all to either go out and buy it or maybe ask somebody else to buy it for you. Anyway, it's a wonderful book. So my aim in these lectures is to try to give some sense of, because this theory involves a massive amount of terminology and notation, which is kind of overwhelming. And so I want to give, maybe hopefully by using certain illustrative examples to bypass having to give general definitions, just to give a sense of what actually is going on in this theory and what kinds of things one can do with it. And maybe the main point I want to drive home is that buildings are not the main point of theory, right? Whatever a building is, it's a combinatorial tool to organize how we may study certain pieces of the subgroup structure, but the actual real meat of everything more involves this certain kind of integral group scheme structures. In any event, we're going to see this play out with a variety of examples, but I just want to stress that the theory is not primarily about buildings, but about something involving integral structures. Okay, so to start off, we're going to take, at least for the beginning part today, maybe most of today, K will be for us a non-Archimedean local field, and it's going to have a finite residue field that, this is my attempt at a Gothic German F. And G will be some connected reductive group over K. Here are some classical examples. And in some sense, for the development of the theory, the group, roughly speaking, doesn't really change. But for various technical parts in the middle of proofs, one sometimes may want to change the group by maybe a central isogeny or other things. So there's a certain amount of flexibility involved. On the other hand, when the group is simply connected, many definitions simplify dramatically. And so for some purposes, I may focus on the simply connected case, simply so I don't have to introduce a lot of extra hypotheses or notation. But in the end, the results really carry over for a general reductive group. And we have this general philosophy from Harishchandra, right, that there's only one reductive group, G, and we should just do everything for all groups at the same time by a uniform method. It doesn't always work out that way. Sometimes we have to do casework. But nonetheless, the goal, hopefully, is to be able to treat all reductive groups in a fairly uniform way, at least for the statements of results, if not always in the proofs. Anyway, this is our general setup. And whoops, let me, okay, so what we want to do, maybe just kind of as a warm-up, so there's a lot of interest in complex representations equipped with an action by the group G of K, where these representations will typically be infinite dimensional, and they will usually satisfy two properties. So one is a so-called smoothness property, which is the condition that the stabilizer of every vector is open, so for all vectors in V. And this has as a consequence, every open subgroup of G of K contains inside of it compact open subgroups. And the reason is simply that every G can be put inside of a GLN as a closed subgroup, and GLN of K, by inspection, has a neighborhood basis of 1 consisting of compact open subgroups, namely the congruent subgroups modulo higher and higher powers of the maximal ideal. And then if you intersect with G of K as a closed subgroup of GLN of K, then that compact neighborhood basis gives rise to a compact neighborhood basis here. Okay, so we have these compact open subgroups that stabilize every vector. And the other property of the representations that are widely studied is a kind of admissibility condition. which is some finite dimensionality property that for every compact open subgroup of your, so for all compact open subgroups, script k inside G of k. Okay, so in particular, as you know, this is of course the huge focus in the local Langlands program is to try to give some sort of useful way to describe or parameterize or study smooth admissible representation, satisfying irreducibility and other conditions. And one way in which this is often done is by trying to find large compact open subgroups for which there may be an interest, a non-zero space of invariance, and maybe organize your classification based upon that. Regardless, the point is that in the study of these kinds of representations, it's important to have some handle on a reasonably large class of compact open subgroups, how to classify the possibilities up to conjugacy, how to understand their internal subgroup structure. So there's a fact which in this context over local fields, I think was originally proved by Langlands, which says that so the question is how to, in some sense, organize such K. So maybe for a specific group like GLN, we can write down some very specific, interesting compact open subgroups, but for a fairly general G, or even for things going away from GLN, how do we understand these up to conjugacy? So Langlands gave an argument to show that every compact subgroup lies in a maximal one, a maximal compact subgroup. And these guys are all open. Okay? So that's nice. So every compact subgroup lives inside of a maximal compact open subgroup. And so we could ask, can we describe these possibilities? So for instance, are these maximal ones, are the maximal K all conjugate? Right, over the real numbers, right? This is a fundamental fact in the theory of Lie groups, right? If I give you any Lie group with a finite component group, then every compact lies inside of a maximal one, and the maximal ones touch every connected component, and more importantly, they're all conjugate to each other. Okay, so one could ask whether this is true in this context. So the answer is no, it fails quite badly, and we'll discuss some examples of this. And Bruhat-Tits theory gives a way to sort of understand what's going on. But the first example I want to look at, simply because it's going to set the stage and be useful for other purposes later, is I want to look at the case of GLN. So in the case of GLN, by a lattice argument, in fact, it is true that all K are in fact conjugate, a GK conjugate to GLN of O. So I'll write O, little o for the valuation ring of K, of little k. So every maximal compact is conjugate to the first thing you would write down. But I think what's sort of going to be useful about this for our purposes later is let's think about the other conjugacy classes. So if I pick, and maybe I should mention, this thing turns out to be, by the same lattice argument that proves this turns out to also be its own normalizer. So if you pick something in GLN of the field that does not lie in this subgroup, and you conjugate it, you will get another maximal compact subgroup. And I want to point out the following. So if we pick something in GLN of K that lies inside, so I'm going to call this K0, and it lies outside of K0, then I can think about GK0, the inverse inside of GLN. So this is different from K0, but it is itself, you see this guy, you say, oh, this is nice because these are the integral points of some kind of integral structure on this group that begins life over little k. So what about this conjugate? So for this conjugate, we can introduce another integral structure on the group. So if we do the following, so we think about GLN over K, and we use conjugation by the inverse of G to go back to GLN over K. Now this sits inside GLN over O. So this is an algebraic group over K. This is a group scheme over O. And in this way, this identifies this is a smooth affine group over O. And its generic fiber is identified with our original group, but not via the identity map, but via the intervention of this. So this defines what we're going to call an O structure on our original algebraic group GLN over K. And by an O structure, what I mean is some script G, which is going to be a smooth affine O group equipped with an isomorphism between its generic fiber and G in such a way that when I form the integral points of this, I literally get the thing that I started with over here. So maybe I'll call this thing this K, script K. And so if I consider this as an integral model for this via this composite map, then the integral points of that is exactly that K inside the original Asher points. Anyway, the point I'm just trying to make is that when we talk about an integral structure over O for something over K, it's an object over O along with a specified isomorphism of its generic fiber with the given G over K. And so I can build something which abstractly will still be the same O group, but the way that its generic fiber is identified with our original G is not by the identity map. It's via this conjugation. And if you set it up that way, and you calculate the integral points, and then you see where they go in here under this, then you get exactly that. So another way we could think about these conjugate copies is that they, in some sense, arise from other integral structures on our group different from the standard one, even though the underlying O group is abstractly the same, but the way the generic fiber identification goes is different, okay? Nonetheless, my main point is simply that in this situation where everything is conjugate, we can reinterpret the different conjugate subgroups as integral points of some other O structures on the same underlying K group. Okay, this is kind of a key point, because we're going to see when we go on to more complicated groups that the O structures that arise will be much more involved than in this simple case of GLN. Okay. That being said, let me make one other observation that can be done using these integral structures. So what leverage do we get by using these integral structures? So let me just point out that if you take GLN over O, then you have a map to GLN over the residue field. And inside of here, you have various interesting subgroups. So for example, you may have a parabolic subgroup P inside the special fiber of GLN over F. And if you take the preimage of that, I'll call this H, then you get various other, of course, non-maximal, I mean, if you take this to be like a proper parabolic, then you get these various other compact open subgroups by taking the preimages of parabolics under this reduction map. These are going to later be seen as examples of what will be called parahoric subgroups. Certain non-maximal but interesting compact opens. Anyway, the point is the presence of the integral structure, the key feature it allows is if you have some object over O, then you can look at the map to its rational points over the residue field. And then if you have interesting things over the residue field, you can take their preimage. And that gives you some new things in here. Okay? Now, since these guys were also arising as O points of something, you could do something similar there. Okay? So that's the one nice thing with O structures is the presence of an O structure on a situation gives some way to take information over the residue field and somehow relate it back and make constructions over O and then over the generic fiber, like making these new compact open subgroups inside the rational points. Okay, but there are some problems with doing things over this residue field, which is this residue field is a finite field. And you might think that finite fields are fantastic, and of course they're wonderful in many ways, but finite fields have a major problem, which is that they're very tiny, and correspondingly, if you're trying to probe some algebrogeometric structure over the residue field by only looking at rational points, then you don't have much to grab onto. Okay, so this is kind of going to be one problem. So this finite f, the finiteness of f makes using f points in some sense too weak for probing algebraic geometry, so algebrogeometric problems, algebrogeometric properties over the residue field. So we would like to, we're going to be building these O structures, and we're going to want to understand features of their special fiber, but we're not going to be in situations as explicit as GLN. And so working only with the rational points over the residue field will not really be sufficient. So for a variety of reasons that I can't get into at this point, but we'll see coming up a bit later, we will really need to be able to carry everything out, not only with our local fields, with their finite residue field, but we also need to, in some sense, pass the situations where there's an algebraically closed residue field, right? As one knows from experience with algebraic geometry over fields, if you're over an algebraically closed field, then calculations done at the level of those rational points is really rich enough to study the geometry of things. But if you're over a finite field, you're only looking at rational points over a finite field, it's not really enough. So in some sense, we need to, in some sense, pass to the algebraic closure of the residue field, i.e., work not over the original residue field, but over its maximal and ramified extension. Okay, so this thing I'm going to call, just for consistency with the notation in Gopal's book, we'll call the maximal and ramified extension capital K, and its valuation ring maybe capital O. In any event, so if we pass to the maximal and ramified, then we will have algebraically closed residue fields, which will be technically very convenient. But then, of course, we've lost something, which is these are no longer locally compact, right? They're also not complete, right? So let's not worry about the non-completeness, but the main point is, in order to, the question is, well, what are we studying over these fields? We're not studying compact open subgroups because these fields are not locally compact, so compactness is not really the right notion. So to do this, we have to recast compactness via boundedness. So if I give you some affine x sitting as a closed subscheme of some affine space, then of course x of k is thereby sitting inside k to the n, and then of course talking about bounded subsets makes perfectly good sense using the valuation topology on little k, all right? And one can show by a short argument that if I give you an affine K scheme of finite type, for any two closed embeddings into affine spaces, the notion of boundedness you get on the rational points using the inclusion is the same, okay? And this is a good notion, even if little k is replaced with this maximal and ramified extension. So over the local field, boundedness is equivalent to compactness, but over the maximal and ramified, boundedness is the good notion to work with, compactness is not useful at all. So we'll typically talk about bounded open subgroups or maximal bounded open subgroups rather than maximal compacts, and that will allow us to do things over the maximal and ramified extension. And this has the main technical advantage that it will make the residue field algebraically closed, which is convenient for knowing that certain calculations at the level of rational points over the residue field is in fact enough to probe the algebrogeometric properties of the things that we're going to be studying. So that's one thing to bear in mind. So another one, well, okay, I'll just leave that there. So maybe we'll just make that the remark. So just bear that in mind that we will need to go beyond local fields to have an algebraically closed residue field. But let's now turn to the next example, which is SLN. Okay, so now for SLN, something very, very interesting happens. Well, you could say it's either good news or bad news, which is the conjugacy completely breaks down, although in a way that may look fairly mild. So here it turns out that we have n conjugacy classes of the maximal bounded subgroups. Okay, and here they are. So I'm going to consider the matrices. Let me write this gamma m. So 1, 1, 1, pi, pi, pi. So this is m. So here m is anything from 0 to n minus 1. So if I give you such a matrix which has m pi's down at the bottom and then 1's up the rest of the diagonal, let me make this a little bit smaller here. Sorry, just not eat up quite as much space. So gamma m, 1, 1, 1, pi, pi. That's m of those. And then we're going to call k sub m will be gamma m SLNO gamma m inverse. Okay? So these I can describe to you what they look like informally in terms of matrix entries. So you might say, wait a minute, that looks conjugate, but notice that the conjugating matrix is not in the group. The conjugating matrix is in GLN of K, not SLN. So at least it's not a priori evident that this is conjugate. And of course, you have to make a small argument to really prove it's really not conjugate to SLN of O in SLN of little k. But of course, you have to make some argument. In any event, so we have this subgroup that we call K sub m. And so here, so let me just describe it to you in terms of matrix entries. So these are matrices that look roughly like the following. So we're going to have so m n minus m. So if we think about these matrices in SLN, so where the upper m by n minus m block comes from the reciprocal, the inverse of the maximal ideal, and this lower block is in the maximal ideal, and these entries live in the valuation ring. These guys are exactly what that works out to be, and these turn out to exhaust without repetition the conjugacy classes of the maximal bounded subgroups. Okay. So that's a very nice example. Now, you might think this is a bit of a fake example because although I told you these can be shown, of course, it's not obvious by hand, these can be shown to really not be conjugate inside SLN, you might think it's a bit of a fake example because they are conjugate in a larger group, so somehow maybe this failure of conjugacy is not quite so serious. So we will see a more interesting instance of this, more interesting failure of conjugacy with a different group shortly. But let me just say that one really interesting application of Bruhat-Tits theory is to put this calculation in a broader setting in terms of this count. Why are there these n examples? So, so Bruhat-Tits theory will give the following, that for any simply connected semi-simple K group G, so SLN, of course, being a primary example, the number of conjugacy classes of maximal bounded subgroups is exactly the product Ri plus 1, where these Ri's are the so-called K ranks of the K simple factors. Of G. So for instance, for GLN, for SLN, there's only one factor. Its rank is n minus 1, and n minus 1 plus 1 is n, which is exactly the n that we showed over there. Okay? So in any event, so Bruhat-Tits theory gives a very nice way to understand these things and to see where this count is coming from. But more importantly, it also provides a source of integral structures on those maximal bounded subgroups, as well as certain open pieces of them. Here again, like for GLN, you could sort of see the modified integral structure just by using these conjugation maps. So we'll see a somewhat more interesting example where the integral structure is less evident shortly. But let me tell you the visualization that Bruhat-Tits theory gives to this calculation. So let me draw the following picture. So suppose you let S inside of G be a maximal split torus over the base field. So for example, for SLN, you might take the diagonal matrices. And if we consider the character lattice of that torus made into a real vector space, this is an instance of what's going to be called an apartment. I mean, technically, there's a slight variation of this that will be the apartment, but it winds up being naturally identified with this. And the building of the group will contain a copy of this real vector space. In the case of SLN, we're going to draw a picture of this in a moment. And why do I call this an apartment? So ordinarily, when you think about this real vector space, when you're studying algebraic groups, you have a Weyl group action, and you make these root hyperplanes, and then you look at the connected components of the complements, and you study this kind of hyperplane incidence geometry. But here we're going to do something a little bit more interesting, which is inside of this vector space, and let's say here's the origin, not only are we going to have the root hyperplanes, but we're going to introduce parallel copies of these. We're going to look at the hyperplanes defined by a of x equals an integer. We hear a is a root. Okay, so roots act on co-characters given linear functionals, and when you set them equal to 0, you get the root hyperplanes. But if you set them equal to various integers, you get parallel copies. And so you get this collection of hyperplanes. And now we're going to consider the group of reflections through all of those different hyperplanes. Now, if we didn't introduce these auxiliary hyperplanes, if we just consider the ones to the origin, then those reflections would generate the usual Weyl group acting on this real vector space. Okay? In this context here, the reflections through all these hyperplanes will generate some much richer group called the affine Weyl group. So acting on this, we're going to have this thing called the affine Weyl group, generated by the reflections in all of the hyperplanes. And then one can try to write down a fundamental domain for this. In the context of the usual Weyl group, the fundamental domain is a Weyl chamber, which is some cone that goes off to infinity. In this context, because there are so many more hyperplanes, the fundamental domain will actually be a simplex. Okay, okay, or something close to a simplex, right? And that turns out to illuminate this example as follows. So in the case of SLN, if you form a fundamental domain for the action of the affine Weyl group, one instance of it turns out to be a simplex, one of whose vertices is at the origin, and the other vertices are at these, what are they called? These fundamental co-weights, okay? The dual basis to the basis of simple roots for a positive system of roots, okay? So there's a very concrete interpretation of the vertices of this fundamental domain inside of this vector space, and these groups that I'm, sorry? Sorry, n-1, thank you. And these groups, K sub m, turn out to be exactly the stabilizers. So maybe I'll call this point pi 0. So these turn out to be exactly the stabilizers. So this building, which I haven't told you what it is, I drew it here. So there's going to be this enormous space. It's going to have an action by the entire group. This real vector space will sit inside. And when you take the whole group acting on this big space, and you look at this fundamental chamber, this fundamental domain given by this chamber, the stabilizers at these points will turn out to be these. But that interpretation of these groups as stabilizers on these vertices of this fundamental domain for the action of the affine Weyl group will turn out to be a very general perspective by which we can understand many, in some cases all, of the conjugacy classes without repetition. Okay, so I'll come back to this interpretation next time. But in any event, let me just show you what happens if we go beyond the simply connected case. So I'm going to look at PGL2. So whatever the building is, it will turn out that the building of G is naturally the same as the building of the derived group, and it's naturally the same as the building of the simply connected cover, and it's naturally the same as the building of the adjoint quotient. So let's take the case of SL2. So this building for SL2, whatever it is, will turn out to be the same as the building for PGL2. But this action of SL2, you see, over local fields, for example, or discretely valued fields, there are plenty of elements in here that are not squares. So the map from here to here is not surjective. So the fact that this group action on this set, whatever it is, can be enhanced to an action of this is more information. And so if you're trying to compute stabilizers or look at the effect of what's going on, understanding this does not tell you all about this. As algebraic groups, SL2 maps onto PGL2, but at the level of rational points over a local field, this has more stuff, so to speak. Of course, there's a tiny kernel here as well. So what's the use of this? So if we take a chamber for SL2, and we're going to call the, I'm just going to call the endpoints x0 and x1, then it turns out that the action of SL2, any element of SL2 which keeps this segment, maybe it carries it back to itself in some way, actually has to fix it pointwise. But in PGL2, there's an extra element which has the effect of flipping this, which SL2 does not do. And one consequence is, you see, if you look at all these examples, these K sub m's, of course, if you send these from SLN to PGLN, then these conjugations all suddenly become elements of the group. And so very loosely speaking, it looks like there's some collapse of conjugacy classes. But it turns out here, you have this point in the middle. And it turns out that in this case, PGL2 of O, and then PGL2, so this turns out to be the stabilizer of this point. So this is GK stabilizing one for a particular chamber. And this, on the other hand, if we consider the stabilizer of this point in the middle, this is a kind of new maximal bounded subgroup, which as a group looks totally different from this one. So you see, in this example for SLN, we see that all of the different guys, they're not conjugate in the group, but abstractly, they're all isomorphic to each other. In this case, the groups are really not the same at all, okay? So we get rather different structure. So even though the building is actually the same for SL2 and PGL2 once we define what it is, but actually the group actions include different amounts of information. And one consequence is that when you try to do these stabilizer calculations, that you will get somewhat different ways of organizing where are the maximal bounded subgroups. So this recipe using the vertices in the SLN case is typical for the simply connected groups. But once you go beyond the simply connected case, something like PGL2 or PGLN, or special orthogonal groups, for example, then relating the conjugacy classes to the geometry of how the group acts on the building becomes progressively more complicated. Okay, so that's just something to bear in mind for what's coming later. Okay, but let me point out one other interesting thing. I want to come back to the integral structures. So in this case, maybe I'll call this thing K0 and this thing K tilde. So it turns out that this K tilde is also, well, it's a maximal bounded subgroup. So it is the group of integral points of some, smooth model from, well, at least I was suggesting before this should happen. We'll discuss this more broadly in a little bit. So this does turn out to also be the integral points of some smooth model, smooth affine O group with generic fiber PGL2. But in this case, if you look at the special fiber of this thing, this turns out to be not reductive at all. This turns out to be just the Borel subgroup inside PGL2 over the residue. Okay. So in any event, the point is that the geometry of the corresponding integral model turns out to be radically different from that of the PGL2O maximal bounded subgroup. So for SLN, we have these different conjugacy classes. The underlying integral models are different as integral models, but as abstract O group schemes, they turn out to be all isomorphic to each other. They're just different copies of the same SLN, but realized with that generic fiber in different ways. But in the PGL2 case, the corresponding O models that one gets are genuinely different from each other. It's not just changing a generic fiber identification. The actual underlying O groups are completely different. Their special fibers are very different from each other. Okay? I would like to give one last example involving SP4. And again, we will come back to this in several ways later on. I think in some ways, SP4 is much more instructive for various things than these type A examples. So let's take the symplectic group. And for me, just for my calculations that I'm going to tell you, my symplectic group SP2N, this is going to be given by the condition where my symplectic form will look kind of like that. Okay, so that's going to be my symplectic group. So 2n by 2n matrices G that satisfy this preservation condition on the symplectic form. So this turns out to have 3 conjugacy classes of maximal bounded subgroups. Okay, so what are they? So 2 of them are going to be related by something that looks kind of like a conjugation action. And then there's going to be a third oddball guy, which is radically different from the other 2. So let me draw the picture of this, this real vector space. So let's draw a picture of the root system. So let's get this. So A, B, A plus B, 2A plus B. So on. So if throw this guy in here too. Okay, and so if you draw in these affine hyperplanes, and you get these extra lines like this, and you get some extra lines like this moving in parallel above and below, and here's going to be my fundamental domain with these 3 vertices. Now this might not look like it, but as you know from your study of squares in high school, this is supposed to be a right angle here. So this is a right angle. So you see this triangle is not equilateral. So these 2 vertices are kind of similar in a way that this is not. And so now if we look at the stabilizers, we wind up getting the following. So let me bring out that triangle here. Let's pretend that's a right angle. I'm going to call this x0, this x1, and this guy here in the center I'm going to call x tilde. And again, if one kind of goes through this machinery of the buildings that I haven't defined yet, and you calculate the action, you wind up getting that the stabilizer of x0 is SP4 of O, the usual thing that you might think of if you try to think of a maximal bounded open subgroup. The stabilizer of x1, I'll call this K1. Well, this turns out, let's get the, so this turns out to be conjugate by the following, okay, I'll say it this way. Gamma K0, gamma inverse, where gamma is 0, minus 0, 1, pi 0, bunch of 2 by 2 blocks as a 4 by 4 invertible matrix. So this turns out to correspond to this guy. Again, abstractly, you see it's a different integral structure using the same underlying O group, sp4, but you've changed the generic fiber identification in a specific way. This guy, on the other hand, turns out to be something much more interesting. So this is a G0 of O, and this guy turns out to be a G1 of O, where here a G0 and G1 are both sp4 of O. They're the same O group, but with different generic fiber identification. So they're different integral structures on our K group. They give us different groups of O points, different maximal bounded subgroups. But then there's the third guy. So the stabilizer in the building, once we define it, that acts on this, maybe we'll call this thing K tilde. This turns out to be the following. So as far, in terms of 4x4 matrices, they have the following entries: O, M, O, 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 M inverse is going here. O, M, O, 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 M, 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 O. Okay. So in this case, this turns out to also be some integral model, O points, but the special fiber is not reductive. It is very different from sp4. This guy, the special fiber, turns out to be non-reductive. And when you mod out by the unipotent radical, it collapses to SL2. So I'm just trying to drive home the point that in this picture, with the simply connected group sp4, there are three conjugacy classes. They happen to correspond in a natural way to the vertices of this fundamental domain by a mechanism that I haven't told you yet. We'll get to that in later lectures. But the point is that the corresponding stabilizer group will be maximal bounded, and it will be naturally the integral points of a certain smooth affine model for our K group. Where that integral structure comes from is one of the key points of Bruhat-Tits theory, and so we'll be getting to that in the later two lectures. Okay. Yes? I'm sorry, yes. Pi is the uniformizer of the local field. I apologize. Yes. Sorry. I'm taking the special fiber mod the unipotent radical. So this turns out to be a non-reductive group. This SL2, I'll use my colored chalk. So if you take, those four matrix entries looks like a slightly non-standard SL2 conjugate, and that's related to this SL2. Okay, so fantastic. So anyway, so these are some kind of basic examples. So now let me tell you lemma that connects up maximal bounded subgroups to integral models. Okay, so maybe we'll, so at least we'll get one proof in today. So here's the lemma. So let's script K inside G of K be a maximal bounded subgroup. And here G is any connected reductive K group. Okay? The statement is that this guy is G of O for some O model, or some O structure G. So every maximal bounded subgroup really does arise as the integral points of some smooth affine model. So let me show you. This turns out to have a very elegant proof. The idea of the proof is simple, but it involves one serious technical ingredient. I just want to stress one thing, though, that although Bruhat-Tits theory is going to make crucial use of these kinds of integral structures, and I warned you before that if we only work over finite residue fields, probing the O points will really not be enough to pin down this thing uniquely. So let me just warn you, from this statement alone, there can be, and I'll show you by example, these things can be changed without changing the group of O points. So this statement alone does not determine script G, but if we allow ourselves to go up to algebraically closed residue field, then it will turn out to determinate, although I may have to discuss that at the beginning of next time. But let me tell you where this comes from, just so you see that there's some natural relationship between maximal bounded subgroups and integral models. So the idea is very beautiful, very simple. So let's pick a closed embedding of G into some GLN. Okay? And so then, excuse me. Now we know that, so we get this G as a closed subgroup of GLN of K. And so correspondingly, this K here goes over to some bounded subgroup inside here, right? This is closed in here, bounded goes to bounded. Well, so inside here, we know every bounded lives inside of a maximal bounded, and the maximal bounded, as I said, are conjugates of GLN of O. So if I change this by a conjugation, then I can arrange that this lands inside GLN of O. So we can change this. So change rho by a GLN K conjugation so that K lands inside GLN of O. Okay, so then what? Well, now something very interesting happens. You see, what happens if we take G of K and we intersect it with GLN of O? Well, on the one hand, that contains script K by design. So here we're using our knowledge of the maximal boundeds inside of GLN. Okay, so now this guy sits inside this intersection. Now, on the one hand, excuse me, this sits inside G of K. This thing, right, this thing is a bounded subgroup. Why is it bounded? Because this thing sits inside GLN of K, where this is a bounded subgroup. So therefore, this subgroup of that is bounded. So this is bounded. The notions of boundedness here and here align well because G is closed in GLN. Okay, so this is bounded in G of K, but I'm giving you that this is maximal bounded. Therefore, this must be equal. So this is maximal bounded. Therefore, this must be an equality. Well, why is that useful? Well, let's now take the way that G sits inside GLN. So G sits inside GLN of K, and that in turn sits inside GLN of O. Now we have this operation in algebraic geometry called schematic closure. So this is open in here, this is closed in here. If you take the closure of this in here, then you wind up getting a model for this over O, where these things have the same generic fiber. So this thing is the schematic closure of G in GLN of O. And so this thing here that I'm calling script G is a flat affine O group. And from the construction, it has the same generic fiber. So it's a kind of a model, an integral model for what we want. And its integral points, if you unravel how this is made, are exactly the intersection of the rational points of this, sorry, the rational point of this with the integral points of our integral structure. So this is exactly G of K intersect GLN of O, which is exactly our script K. So this almost does the job, except for one huge problem, which is that this script K is not generally smooth. It's only torsion free. So in concrete terms, the coordinate ring of this guy is just the image of the coordinate ring of GLN inside the coordinate ring of our given G. So it's some O algebra finitely generated living inside of a K algebra. So it's torsion free, so it's flat, but typically this is not smooth. So usually this script G is not smooth. Now this might seem like a minor issue, and in some ways it is if one knows a certain tool, but the point is we now have to apply a hammer, which is that there's something called Néron smoothening. So there's a systematic process that Andrei Néron developed in his development of the theory of Néron models, where if you start with something if you start with some scheme of finite type, flat over your valuation ring, it does a systematic process which in some sense improves the special fiber, and the generic fiber is smooth, and it keeps improving the special fiber, and finally many steps, it eventually yields something smooth. The thing is completely canonical. So the point is, this produces something I'll call G smooth mapping to G, where this guy, because our original thing was affine, this will also be affine, smooth affine O group, where these have the same generic fiber, but this guy and the same O points. Okay? So the neuron smoothening is in fact the thing that the lemma is asserting exists. Very good. Okay? So that shows us that maximal bounded subgroups always come from smooth affine models. You put it in GLN, take the intersection, take the schematic closure, smoothen it. Okay? But as I warned you, this context with finite residue field doesn't pin this down uniquely. Okay? So at the beginning of next time, we'll discuss kind of how we get around that issue and the issues around connectedness of the special fiber and things like that. And we'll talk a little bit more about what the building actually is and what properties it has and what kinds of things an understanding of this building and its group action allow us to make about the structure of the group itself. Okay, so we'll discuss some of the potential applications, which we'll get to in the third lecture next time. But really the main focus of next time is I want to talk a bit more about these integral models and then introduce the building and discuss how thinking about the building, whatever it is, allows us to understand these weird non-conjugate subgroups that we were making before and how to probe deeper into those using other kinds of integral structures. Okay, stop there.
So, any questions?
Sorry, so the question is, do all integral models arise in this manner? Yes, so the answer, yes. So just like over a field, every affine group scheme of finite type over a field is a closed subgroup of the GLN. So similarly, one can show over a Dedekind domain, in particular over a PID, like O, every smooth affine, every flat affine group of finite type is closed inside of some GL. So any integral model, whether flat or smooth, for your group will in fact arise as a closure in a GLN, if that's your question. Oh, sorry. Yeah, sorry. Okay, you're right. Your question was, are they right? Are these things always maximal? Great question. I was going to get to that later in my notes, but since you brought it up, let me answer it now. So the answer is no. So that's a very important point. That so G of O inside G of K is usually, it's always bounded, but it's usually not maximal. So let me tell you good news and bad news. Okay, so on the one hand, if the special fiber is reductive, then Bruhat-Tits theory will guarantee that it is in fact always maximal. Okay, but when it's non-reductive, this fails. And let me just tell you one way that you can start with any example and make another one which kind of takes out the maximality. So here's the construction you can make. So take your favorite group, and let's introduce what I'll call K plus, which will be the stuff that reduces to trivial on the special fiber. So just take the kernel of reduction on your integral model. So I claim that this is also the O points of an integral model. And of course, it's typically not equal to this, right? This is usually, yeah. And the point is, so K plus turns out to be G plus of O, where G plus is what's called the dilatation of G along the identity point in the special fiber. So there's an operation that if I give you, if you have something over O and I give you a closed subscheme of the special fiber, there's this operation called dilatation, which is basically an affine piece of the blowup along that thing in the special fiber. But what the property it has in this nice smooth setting is that at the level of O points, the only O points that survive to the dilatation are those that landed in the thing that you dilated along. So if you do this thing at the identity point, you will wind up getting, and what you get, and if you start with something smooth, and when you dilate along is also smooth, the output of this is also smooth. So you will get some other smooth model, but whose O points are only those that reduce to the identity point. So that's an example where you have the O points is not maximal as a bounded subgroup. Yeah. So we'll talk about this next time. All of the maximal ones, in the simply connected case, they will be the stabilizers of the vertices of a chamber. But anyway, we're going to be talking about this next time.
Any other questions?
Yeah. GLNO to GLNF. Yes. Yes. The inverse image of those, yes? Yeah. That just meant the inverse image of the parabolic. Yeah. So when we define what parahoric subgroups are, these will be certain typically non-maximal, but roughly speaking, they're going to reduce to parabolic subgroups of some other things. Anyway, we'll put that into broader setting later. Sorry? Yeah. Because it's exactly, if you unravel what schematic closure means, it literally just means you have this guy mapping to this guy at the level of coordinate rings, and it's just the image of this. So it's some O subalgebra of this. So it's torsion-free as an O module.
Any other questions?
Yes. No. So for PGL2, there are two conjugacy classes. One, which is that of PGL2 of O, and the reduction is PGL2. And then there's this other one that corresponds to the midpoint, and then the reduction of that is kind of roughly a Borel over the residue field. Yeah. So the structures, but this is a very typical feature no, right. So type A is extremely misleading. So for SLN, like the examples I gave, those are exhaust all of them, and they're all reductive models. And this corresponds to what's called all the vertices are special. And this is basically because the affine diagram of type A is a circle, and so it's like all points are created equal. There's a huge difference, yes.
Any other questions? Okay, so we thank Brian again.